think it's fine. Okay, this microphone is working. Yeah, okay. So we'll start the seminar. So this is the first seminar of the year, and we're going to do a few more later on this year, but today it's about binary exploitation. So it's about corrupting memory and what you can do with it and how you can break programs. So we're going to be talking about a few things. It kind of assumes a little bit of knowledge about reverse engineering, but we'll also cover some of that later. We're going to talk about stack smashing, which is overflowing the stack and how you can corrupt stack memory. Also, certain types of exploits where you can insert your own code, which is shellcode. We're also going to talk about return-oriented programming, which is controlling hijacking control flow. A little bit about heap. I didn't go too deep into heap. We'll just cover the basic vulnerabilities and then some other techniques as well. So we are doing pretty good on CTF time. So we're probably going to play a CTF this weekend. If not, then we'll just do it next weekend because I don't think there are any CTFs that have weights. So we'll see, but there might be a high school CTF we play this weekend. And it's not going to be fair, but it's going to be fine. So yeah, there's not many people here, so I'll just go into it. If you have like a little bit of background in reverse engineering, you can sort of skip this, but we're just going to talk about how programs are set up. So you have a program on your disk. We're going to think about the ELF file format. There's different types of executable formats, but we're going to be talking about the ELF format. So you have these headers and sections and segments in the ELF format, and these are specifically going to be mapped into memory. So when your program is loaded into memory, you gain a few extra sections. You gain the stack, you gain the heap, and you also gain segments for the initial code and then the initial data, and then some memory later on. So there's a little bit more segments as well. Let me just check the recording. Yeah, okay, the recording is still happening. Okay. And yeah, so when your program gets loaded into memory, you get a bunch of space for different segments of your program. You get some libraries to stack in a heap and then some other regions as well. So the text segment, I think we'll cover that right now. Oh, what? Well, you can view all of these segments in infoproc map. It's the mapping of the memory in your process, or you could use VM map as well. And you can also find it in the proc folder of your Linux device. But yeah, so the text section. So the text section is the part of the program that has all of your assembly code, the executable code. So you can view it. It's just some part of the bytes in your program. This is actually on the disk, so it's not in the memory, but it's going to be one-to-one mapped back onto memory. So the text segment is all of your instructions, and it's machine code. So we can often convert this machine code into assembly. Why is it so slow? Okay, yeah, so we can often convert the machine code into assembly, and assembly is just our understanding of the machine code. So it's meant to be human readable. So for example, this machine code here, these bundle of bytes, it means compare RDX REX in assembly. So you're comparing two registers against each other. And we can use different syntaxes. So the syntax that we are going to use for this presentation is the Intel syntax. There's also the AT&T syntax, but the Intel syntax is a lot more succinct. Hello. So there are like different segments as well. There's data and then unknown data and then like read-only data as well. So this is somewhere in your program. This is for like strings or like constant variables. These aren't like, they're just strings or like constant variables, things that you know ahead of time and they're stored somewhere in the program. There's also unknown global data and yeah. So you'll see this somewhere in your program when you actually load it into memory, or you can see it on the disk as well. And there's also this global offset table. So whenever you have a program, you're going to have a few functions, And functions are going to be sometimes declared in different libraries. So we don't actually know the address of the libraries, but you have something which is the global offset table, which will store a few functions. They're called PLT stubs. These are functions that will find the address of the library. So you'll see later on that when we actually debug a program, you'll be calling into these PLT stubs versions of the function. So we'll call into a PLT version of puts, and then the PLT version will find the actual address, which is somewhere libc, probably this. And yeah, it's usually used in position independent executables, which we'll get into later on as well. But this is another section that you might see sometimes. And then you have syscalls. So syscalls are specific functions that the operating system uses. So when we look into the assembly of a program, there are going to be places where we have to interact with some operating system specific things like opening a file or writing to a file or getting the time or like accessing the program memory. So if you want to actually invoke some of these syscalls, you have to use bytecode and invoke them like that. So we'll show an example of how you can invoke a syscall. There's this really cool website down here, x86syscall.sh, for the x86 syscalls, like how you can actually call them with the x86 assembly. So we have this syscall here, which is open. Essentially, it opens a file. So what we're going to do is we have to give it the pointer to a file name. So we have to get the pointer to a file name, which is essentially a string. A string? Yeah, I think it's a string. So what we're going to do is we are going to load that value into RBX, and then we are going to push this value onto the stack. So we get an address, and then at the very end, we are RSP. So RSP is the stack pointer. So we get the pointer to the flag string. So that's RDI. So that's how we get RDI, which is a string or pointer to a character array. And so this would be flag. And then we also have RAX, which we can just directly set as 2. And then RSI, which is the type of reading mode. So you'll see a few register manipulations before a syscall, and you can see what it's actually doing with this website here. And yeah, so essentially what the syscall is doing is it's opening the file located at /flag, and it's opening it, and then it would return a file descriptor pointer. Okay, so now we'll talk about the stack. Now the stack is kind of important for binary exploitation. Real quick, I'll just check Discord if there's any issues. No, it looks fine. Okay, looks fine. So the stack is very important for binary exploitation because it is where you can actually input things. So every single data in the function is going to be located into the stack. The stack is responsible for the data within functions and also the other functions that you're going to be jumping to. So again, it's a section of the virtual memory. This is everything inside of the RAM, and the stack is just a segment of what of the program memory. So you can actually view this when we use a debugger. You can actually view the values onto the stack. Okay, so a stack frame is a portion of the stack. It's a subset of the stack, and it's responsible for all of the functions, or the info about the current function. So it's responsible for managing the information with the current function. You can store information about the local variables in the function or the return value of the function. So after you finish a function, where should we return to? And it's defined by 2 pointers. So there's the stack pointer, which is the top of the stack, and then the bottom pointer or the base pointer, which points to the bottom of the stack. So essentially, you can change these pointers and then change the size of your stack because the stack is only defined by these 2 pointers. And that can cause some issues later on as well. But this is generally what we expect. So most things, when we actually want to take values from the stack, we're going to be doing some manipulations from these pointers, like adding some value to the pointer to access, like let's say this value here. We add some value to RSP, and then we can get this value here. We can dereference RSP and then get this value here, 0x70. So yeah. Now, how do we actually call a function? And we're going to be calling a function in assembly, so how is it actually set up as a call? Well, every time a function is called, there are 3 steps. There is a prologue, a function body, and an epilogue. So the prologue is how we set up the stack pointers before we enter a function. So what we're going to have to do first is we're going to have to push the base pointer and then reset the stack frame. So set the distance between the stack pointer and the base pointer to 0, which is make them equal to each other, and then allocate some space for the local variables onto the stack. And then the epilogue is going to restore the previous stack pointer, and then it's going to restore the previous base pointer as well and return to the caller. So I'll show you an example because that was a lot of stuff. We'll just have an example of how we actually run a program. So this is, on the left, we have the source code of the program. We have a function here which is void a, so it's not going to return anything. And on the function, there's a local variable which is this integer a, which is equal to 10. And then we have our main function, we're just going to call a as well. And then on the right side, we have this assembly. So all of the assembly is here, and we'll just go through all of this assembly as we talk about it. But when you compile the program and then you have the actual object file and then you disassemble the object file, this is what you'll see. Okay. So yeah, okay. So we start off in the main function. What we're going to do is we're going to have the prologue. So before we actually enter the function a, we're going to have our prologue. So we're going to reset the stack. So we're going to set the stack size to 0. And that essentially means that we make sure that RBP and RSP is the same. So we move the value of RSP into RBP. So let's just say they have the values 0x3000, 0x3000. So they're the same thing. What we're going to do after that is we're going to do the call. So we're going to call this function. And what we do when we call the function is we actually put the return address. So the return address that we're going to be going to is this line afterwards. So we put that onto the stack somewhere, and then we call into the function. So we're going to call into the function, and yeah. So we call into the function, and then we push a value onto the stack. So we push the base pointer onto the stack. So remember, the base pointer is 0x3000, so we push that onto the stack. And when we push onto the stack, our stack increases in size. So RSP is going to point to a different value onto the stack now. It's going to point to the newest pushed value onto the stack. Then we're going to reset the size to 0. So we're going to set the size to 0 because now we're working within our local function. Then we're going to allocate a few spaces for local variables. So we're going to subtract RSP by some value, and this value is going to be the entire size of our stack for the local function. So we subtract it by 16 bytes. Okay, now we can actually start to do the function logic. So in the function logic, what we're going to do is we're going to set some of the values that we passed in onto some stack variables. So we're setting up the stack variables here. At some offset from the stack pointer or the base pointer, we're going to be putting this constant value a. And why is it doing a? RIP. Why is it doing a? This might be a format string thing, or we actually might be printing it. 0x a, oh, 10. Integer a is 10. Okay, yeah. So this is the integer a, yeah. Okay. It has a value of 10. And then we are moving 0x61 onto the stack as well. Oh, I think this might be a character. Yeah, this would be a character. Okay, the original source code is actually wrong. Okay, that's my bad. Okay, but we're putting a character onto the stack as well. Essentially, the main thing that you want to know is that, okay, all of the local variables are going to be between RSP and RBP, and then we can like directly access them as an offset from RBP and RSP. And then this is just doing puts. So this whole segment, you don't have to worry about it. It's just doing the puts call. And then after that, we are going to leave. So what is leave going to do? Leave is going to change the stack size to 0. and then it's going to return the original base pointer. So we're going to delete all of the stuff that we have here, and then we're going to return the original base pointer. And this is the same as what we had before we called the function, so that's the epilogue. And then what return does is it sets the value of the base pointer or the current pointer to the value of the base pointer. So we essentially return to our return address, and we return to the return address here. So that's calling a function. Maybe we'll have a few more examples as we actually debug something, but the main point is that we are doing everything as an offset from the stack pointer and the base pointer. So this is something else that is important. When you're working with programs that are made for different architectures, you have different calling conventions. So whenever you call a function on a 32-bit binary, you have to pass arguments through the stack. So for example, this function here on the left, we have a function, myFunction, and then you're passing the arguments 4, 5, and 6. So how this looks like in assembly is we're going to be pushing the value of 6, 5, and 4, and they're in reverse order because we had 4 here, but then we're pushing it at the very end. And then when we actually go into the function, we are grabbing them from an offset from the stack. So we're grabbing 4 first, then 5, and then 6, because we can pop it like that and then have the same order. So this is how you pass arguments on 32-bit binaries. On 64-bit binaries, it's actually passed through the registers. So if you're passing one argument, then it's going to be through RDI. If you have a second argument, then that second argument will be an RSI. So these are just registers. And then any extra arguments will be pushed onto the stack, like the 32-bit version. They're going to be pushed onto the stack. So yeah, you can see here we have the same function, but now we are going to be moving the values into registers. So the register EDX is going to have 6, ESI is going to have 5, and then EDI is going to have 4. So we're passing by registers. And then in the function, we are moving these register values onto the local stack frame for the local variables. So yeah, so that's about the stack. Is there any questions about the stack? I kind of rushed it over, but yeah, the stack is kind of important. We talked about how the stack actually works with assembly, but maybe we'll get some conceptual understanding later on as well. Presentation posted. Let's see. I can give you the slides right now. I think you can. I hope, okay, if I share this, you won't be able to edit it. I'll send you the link right now, though. But yeah, everything we did was some recap on reverse engineering. If you are a little bit hazy on some of the details, there are good resources like Pone College to learn reverse engineering, but we're not going to be doing too much reverse engineering because some of the skill sets are relevant, but the most important part is just understanding assembly. But yeah, now we're going to talk about binary exploitation. So the trademark of binary exploitation is the buffer overflow. So the buffer overflow is, okay, so the buffer overflow is the classic example. Okay, there is input buffering on this program, okay. So yeah, you have a buffer of some arbitrary size, and then some input is going to bypass the size of the input buffer. So it's going to overflow the size of the input buffer. So this can happen in 2 memory regions. It can either happen on a stack or on a heap. And this is a problem because your program expects the memory to be at a certain size, but then the actual state of the memory is going to be a little bit different. So we're going to talk about the stack overflow. The stack overflow is a buffer overflow onto the stack. So if there's no input size checks, which can happen if you use certain functions, then you can be able to override some values. So right here, a stack variable is the buffer, and I could override it. Maybe if we have like a vulnerable function like gets, we can override it with a bunch of values. So what if we spam it with a bunch of A's? Well, what ends up happening is that our buffer can actually corrupt some of the adjacent data in our stack as well. And this is concerning because we can change the return address and also local variables somewhere else in a stack. But we can change return address, which is dangerous because if we know the return address of some other function or some other piece of code in our program, then we can essentially return anywhere we want. So yeah. So let's try to exploit this piece of code. You can follow along with the files here. So these are the files. You can try to download it. We're going to do a buffer overflow on this. So try to download it on your machine, and then I'll run through how to exploit it in like a few minutes. But you can try to exploit it on your own as well. Essentially what we have here is we have a function that's the win function and then another input buffer in our main function. And we want to call the win function because then we win. I think I actually changed some of the challenge a bit, but yeah. So I'll keep this up for 1 minute, and then after that, I will try to solve the challenge. Also, before I solve it, is there any lingering questions about anything about the stack or about program memory in general? Anything I might have skipped over? Yeah. Okay. Okay, so I'll show you. Okay, so when we do this challenge, there will be an example, but essentially, this variable here, the buffer variable here, is a variable onto the stack. And then when we do gets, we are taking the user input and then putting it into the address of this buffer variable here. Oops. And then if we have like a super big input, then it can actually override the space that we allocated for the buffer and change the variables of other things onto the stack. So I can show you with this part right here. Gets is a vulnerable function because it doesn't check the input size. So, okay. So I have the challenge here. If you want to make this challenge, I only provided the source code. If you want to make it, there's a make file here. And what you do is you do make all, and then make all will compile the code, and then you get the challenge code right here. Actually, how many of you guys downloaded the challenges? Okay. Well, that's fine. I'll just run through it. It's not going to take super long. It's a simple challenge. But yeah, so the challenge is a little bit different actually. Like instead of printing I've been pwned, it actually executes a shell. So we're going to try to exploit this. So first thing I'm going to do is I'm going to try to find, I'm going to look at the assembly. So I'm going to look at the assembly of the challenge. What this is going to allow me to do is find the local address of these functions. So these are the addresses from the base pointer of our functions. So we have the win function here, and I'm just going to note this down. somewhere here. The win function has an address of 0x4011b6, and then the main function has this address here, but I'm not going to worry about that right now. So what is happening here? So this is the assembly. There's a few functions here like set virtual buffer, but what we're interested in is puts. So what puts returns, or no, not puts, gets. What gets returns is the pointer of the place that we input our data. So I'm going to try to break at this function here. So I'm going to use a debugger. I'm going to use GDB on challenge, or actually no. I'm going to use pwn_debug challenge. Essentially, pwn_debug is it's like a plugin for GDB that allows you to see a bunch of like the stack and a heap and like a whole bunch of other things, and it's very nice. So I'm going to disassemble main and see what I have. So this is the same assembly that we had earlier on, and then we have the gets function here. So I want to break at this gets function. So it has an offset of 94. So I'm going to break at main plus 94, and then I'm going to run my program. Okay, so over here. Okay, so it calls gets, and then I'm going to have to give it some values. So let's just flood it with some A's. And then after that, gets should return some address in REX. So okay, so after we call gets, we get the pointer to wherever we stored our data in REX. So this is the value of it. So if I examine the memory at this area, it's 0x61111 and 61111, and this is just A. So this is the hex value of A. So this is an A here, and this is an A here, and it has continued quite a lot. And then after that, so I'm gonna take note of this. I actually have to check if I run this program again, is the address the same? But yeah, so we're gonna continue on. We'll just like continue on a few lines. So I'm doing next instruction all the way until the return call. So this is move EAX0, leave, and then return. Okay. So return is going to be here. Actually, X. Okay, so it's going to return there. So what return does is it checks the value of RSP, and then it will change our instruction pointer to this address. So right now RSP is this value here, and we want to change it to the value of the win function, the value of win. So what I can do in the debugger is I could set RSP equal to this value, and then if I do the next instruction, then I will be in, which function will I be in? Probably not. Oh, segmentation fault. Okay, never mind. Okay, we're gonna do something, and we're gonna try to find how we can actually override this return value. So I'm gonna run pwn_debug again. I'm going to make a new terminal. I'm gonna make a new terminal, and I'm going to generate some input. Let me actually exit out of here. Source then bin activate, and then Python import pwn. So I'm using a Python library called pwn_tools, and what pwn_tools is going to allow me to do is it's going to allow me to generate a cyclic string like this. And what I do with the string is I input it into the program whenever it asks for it, So let's see where we are. Disassemble main. I'm gonna set breakpoints. Okay. I'm gonna set a breakpoint at main plus 126. Or no, delete that. 126. I'm gonna set a breakpoint right before the return, and then I'm gonna run the program. And it's asking me for my post, so I'm gonna give it this value here. And then I am here right before return. I am going to go down a few lines, and then return has a different value now. So if I print out RSP, I get this value here, which is the hex of FAAB, I think. So these are some values that we inputted from this from our input previously. So our input was this, and then FAAB is somewhere down the line. It's somewhere, it's right here. FAAB is right here. So we're gonna find out the exact offset this was, because at some point our input was overflowed, and then this value corrupted the return address. So we're gonna try to find where that was. I think it was 66616162. Okay, so we're gonna have to find, oops, cyclic find 6 plus 0x61 62. Okay, so this is 120. Okay, so that makes sense because, yeah, because the buffer address was 100, and then we have 8 bytes for the return RBP, and then a few more somewhere along the line, probably for saved temporary variables. But 120 is where we have 120 bytes after our input is where we start to overflow. So I'm gonna have 120 bytes of A, and I'm gonna add my own bytes. Let's say x22, x33, x34, x55. Okay. So we have that. Actually, okay. No, let me do this instead. Okay, so I'm gonna send this as an input instead. And if it's correct, if the offset is correct, then the return address should have the value of dead. X. Okay, so I think this is the hex value of dead. Yeah, 6461. Okay, that's correct. Okay, so we want to instead replace this value at the end. We want to replace it with the win function, because this is the address of the win function. So you want to return the value at the end to be the win function, so that when return returns, it's going to go to this value instead. So if I try to do that, which would be, do I have pwn? Yes, I do have pwn. Pwn.p64, and then this value here. So this is converting it into little endian bytes so that I can pass it as an input. If I try to pass this as an input to my thing, it's actually not going to be the same value because of the character set that I have when I'm actually inputting things. So for example, if I try to run and then I input this value, the return address is not going to be what I want it to be because it's going to be eating different values. So RSP is not going to be the value that I want. So what I have to do is I have to pipe it in with a different process, or I can use Python. So I'm gonna store this value somewhere, this code somewhere, and I'm gonna use Python to run the program and then send in that input. So solution.py. So we're gonna make a Python script. So the first thing we're gonna do is import pwn, and then we're gonna define a process that we want to interact with. So it's pwn.process, and then the name of the process, which I think was challenge. And then we're going to, do you have to run it? No, I don't think we do. Payload equals p dot binary a times 120 plus pwn.p64 for our return address, which is here. This is the return address that we want. And then we're going to send this as bytes, and we're going to do an interactive after that. I think this is okay. Python solution.py. Challenge segfault. There's somewhere. Okay. So this happens sometimes. I'm not sure what the error is, but I can attach a debugger instead. So on debug with the challenge. I'm actually not sure if this address is always going to be the same. I'll have to see right now. Run. Oh, I see what you mean. Okay, let's see. Also, should I increase the font size? Okay. I do that. Here's 18. Okay. Break. And then I think it was main plus, and then the offset to main was 126. And I'm going to send payload after that. Okay. So what I'm doing here is I have my debugger and my challenge. So I'm going to run the debugger with the current challenge, and then I'm going to tell my debugger that I want to break at this offset from main, and I want to run the challenge, and then the challenge is going to ask me for an input, so I input my payload, and then hopefully I can see what's actually happening in the debugger after 126 offsets from main. So I'm going to 126 text is not in bytes. Okay, so I'm doing 126 because it is right before the return call here. So if I disassemble the main function, so this is the main function. Return is here. So return is an offset of 132 from main, and then 126 is a little bit before that. I could also do this, but I'll just put it before return. So I want to set a breakpoint before return. And okay, so I'm here right now. It should be correct. Instruction. Okay, so return should be going to the win function. If I do this, oops. If I print out the value of, oh, no, that is not right. Okay, if I print out the value of RSP, oh, no, I have to go to, wait, this is return. Okay, should it be going to this value right here? It might be going somewhere else. Oh wait, no, it is going to win. Do I get a segmentation fault? Segmentation fault somewhere along the lines. Okay, well, I think I'll find that out later on. But essentially what we did was we changed the return address to be the address of win, and then we went to it. There could be a segmentation fault. Oh, I see. Wait, no. Bin sh. Okay, maybe I'll just I'll run this again, but if this doesn't work, then I'll skip to the next one. But The main idea was we had to find our buffer and then how much past the buffer we could overwrite the return address. And then after that, we would change the actual value at the end of our buffer to the function that we want to go into, which is happening in the debugger, but we're getting a segmentation fault, which means that we're accessing memory that we shouldn't be, but we'll see what's happening. So we're going to win, okay. It seems fine. So there's a segmentation fault here. What was that? System at PLT. Okay, maybe I can't call system on this machine. I haven't tried that out. But anyways, this should execute a bin sh. Anyways, maybe it's a WSL issue. But okay, we'll just continue on. So the main idea was we had to find how much past our buffer that we would. Okay, sorry about this. We want to find how much past our buffer would actually change the return value, and then we change the return value to the address that we want. So there is a mitigation against this, and our program, well, our solution, it would have changed the return address to some value that we know, like some address that we know. The address that we found was that win should be here, but sometimes when you load a program, this win address will be somewhere completely different. And this is address space layout randomization. So this is a mitigation against these sorts of simple return hijacking attacks. And what this does is it will randomize the location of your program's text, the stack, all of the libraries, and all of that stuff. So every time you run the program, the actual addresses of your code is completely different. So our attack back then wouldn't work. When you actually run your program, you can choose to disable this because it's an OS level protection where it loads your program somewhere. So you can choose to disable it when you're actually running a program locally. But if you're on some program that's remote, then you can't really do this. So what you have to do is you have to try to find the address that you want. So you have to use another vulnerability for that. Or you could try to brute force it. If you have enough buffer space, you could try to brute force it. Or you could use another vulnerability in how processes work. So if you fork a process, the address space will look similar. So if you find the actual address that you want, it could be the exact same as the main process as well. But this is only for certain cases. Like this is true on Android, but it might differ on different operating systems. But just know that ASLR is a mitigation that we consider. And it exists on a lot of programs. A program that is able to work with ASLR will look like this. So a program independent executable is a program that can work with ASLR, and any of the code that we want to execute will execute the exact same way. So instead of like looking at direct like absolute addresses, what we end up doing is we have the RIP, which is somewhere in program memory, and then we add an offset to it. Because the data and the text, they're going to be loaded in the same general section. So you can just add an offset to that. Obviously, we don't know where the stack is. So the stack is going to be set up virtually. So, I mean, yeah, you can still find a stack a completely different way. But if we're accessing data on a position independent executable, you would use an offset from RIP. So that is ASLR, and it's a common mitigation that most programs have. The reason why this program doesn't have it is because we changed the compile flag, which was no pi, and I think GDB also disables ASLR by default, but you can compile a program to not have pi or ASLR. There's a second mitigation, which is a stack canary. So let's say that this is my buffer, and then what I do is I overwrite the buffer, so I can overwrite a bunch of variables over the stack. But then I have the stack canary, which is a value between the return address and my buffer. So all of my local variables will be above the stack canary. And then if I want to overwrite the return address, I also overwrite the value of the stack canary. And this is bad because what the stack canary will do is it will compare the value that is stored somewhere else in storage to the value that it currently has in the stack. And if it's different, then it will signal a termination of the program. So this is an example of compiling a program with a canary and without a canary. And there's a few things that are different. So this is the original source code. It's just we have our main function, which has a buffer of 100, and it's getting user input. So without a canary, it's very simple. But with a canary, what you're doing here is you're grabbing some value from thread storage, so fs0x28. You're grabbing this value from the thread storage, and then you are putting this into RAX, and then you are putting this value from RAX onto the stack. And then at the end of your function, you're going to be comparing the value of this stack canary with the actual value in thread storage. So if the value of the stack canary is different, then it's going to call this function, which is a stack check fail. But otherwise, if it's the same, then you just return. So that's something that we have to keep in mind. There are ways to get around a stack canary. If you can find the value of the stack canary, then you could overwrite to the stack canary with the value that it was before, and then the final check wouldn't trigger. Or sometimes, if you can find a way to overwrite to the stack non-sequentially, so let's say maybe you have an array and then the array has like an offset, you can just directly change from that offset. So if you have methods to overwrite the stack that's not going to overwrite this canary, that also is a way to bypass it. I think now we're going to talk about shellcode. Okay, so shellcode is very powerful. Shellcode is essentially assembly. So it's the machine code that you create for exploitation purposes. So this is my assembly, and this assembly is going to compile to or assemble to some shellcode that when run will open the binsh process. So the reason why this is a problem is because when we execute a program, we try to equate data and instructions. So in certain older architectures, this is not the case anymore, but we had data that is the same as instructions. So we have these pointers to parts of our memory, and they're considered the same, right? Instructions is just bytes data somewhere allowed, and all of these sections is both executable and writable, because you have to execute instructions and you have to write to data at the same time. So if this is the case, then we can change portions of our program to be executable. So what we're going to do is we have some shellcode into our first input, so like a shellcode for opening a shell, spawning a shell. And then what we can do is we can override a part of our memory through, let's say, a Stack Overflow. We can override that part of the memory, and then we can make it so that the program returns to the place where we inputted the shellcode, and it runs that shellcode. So it runs our machine instructions that we set up previously. So I think there's an example somewhere here. Oh no, this is creating a shellcode. If you're interested in making your own shellcode, you have your original assembly file, and then what you have to do is you have to extract the main part of your, or the .text part of your compiled version of your shellcode program. And you can use Python to send this raw shellcode to program. because if you send it by the terminal, then it won't show up. But yeah. So here's another challenge. I hope this one works. It'll show up in a debugger anyways, but this is the second program. It's in the same repository, and this challenge doesn't have a win function. So if we want to spawn a shell or do anything that we want to do, like any arbitrary code, then we have to write our own shell code and spawn a shell like that. So you can download the files here. Yeah, so I'll just give you a few moments to do that. Is there any questions about the previous stuff? We'll try to execute this as well. RIP. Yeah, it is RIP, but I don't know what this is from. Let me see if the solution works for the other one. Okay. Okay, I'll try to do this second challenge right here. So the second challenge we have is this program here. It should be set up the same way. I'll see if I can execute it. Okay, it looks okay to run. Okay, so again, shellcode is just machine code. So any sort of machine code that we give it, it can just run as if it were part of the original program. So I have this assembly code right here, and I want to convert it into machine code. So I can use the previous commands to convert it into a object file. And then if I have the object file, I can extract the text section from it to get the actual raw shellcode. So I did that previously, and then I have the shellcode, the raw shellcode right here. And I can directly input that into a program anyways. But we're gonna go back. Let's see. Buffer, okay. Okay, so it's pretty much the exact same challenge, but I am going to check how much we have to write into it to overflow and change return address. So I'm going to run the program in a debugger. I'm going to disassemble the main function, and then I'm going to break right before the return. And I'm going to run. I have import home. Oh, wait. I think it should be the same to 120 bytes. So we'll just see what the value of RSP is right before we return. Next instruction, X value of RSP. Okay, so FAAB, so this should be 120, okay. So what we're gonna be doing is we want to change this return address to the address of wherever we inputted our code at. So I'm gonna disassemble main again, and I want to, I'm not debugging anymore. The main. Okay, so disassemble main, and I want to find the address of where I'm inputting. So I'm going to break right before this call to gets. Yes. Right before this call to gets, I want to break right before here. So I'm going to set a breakpoint right before there. So break main plus 114. 114, okay. 114. And we are going to run. Continue, and then we're here right now. So I'm going to go to the next instruction, and then RDI is going to be here, and then the pointer to our buffer is here. So we'll just do this, and then it should be the same as here. So this is the pointer to our buffer. I think it should be the same every single time we run the program as well, because there is no ASLR. There's no ASLR in this program, so this address should be the same every single time. So we're going to keep that there. And what we're going to do is we want to change our return address to be equal to the address of our buffer, because what we're going to be inputting into our buffer is code that can be executed. So we want the program to return to our buffer that we control and run the code that we put in previously. So how we do that is, let's go to this one, and I'm going to make a solution port equals process the local challenge. So we're going to be running our local challenge np send line. This should be payload equals to the bytecode. So we have the bytecode here plus some values to make it equal to 120. So like some, okay, we'll do that later. And then p64, and then this address that we want to return it to. And we want to send this payload afterwards. So the bytecode, we actually have it, and it's actually some shellcode. All right, cp shellcode raw. So this is the actual bytecode that we want. We can actually look at the bytes. These are the actual bytes that we want. What we can do with Python is we can just open this file and then read it as bytes, and then we can have that as our payload. So solution.py bytecode equals to, we'll just do this for now, and then with open shellcode raw in byte reading mode as f. Bytecode equals f.read. Okay, so we want to send bytecode, and we want to make sure that the bytecode, because the bytecode is not going to be the entire size that we want. In fact, we want to have about 120 stuff before we overwrite the return address. So we're going to have to make sure that this whole segment here is 120 bytes, so that when we add this, this is going to change the return address. So bytecode, we can just do this, 120 minus length of bytecode times this this random value here, and then the address that we want to return to. So we'll see if this can do stuff. challenge. Oh, pwn.process. Pwn.process, pwn.p64, p.sendLine payload, okay. Stop process challenge here. Okay, I am going to set up the debugger beside it to see what's happening. Because system is not executing here, it worked on a different device, but it's peculiar. But we'll just see what is happening. So I'm going to run it with pwn-debug, and then I want to set a breakpoint somewhere before the return address, and then I also wanted to run it afterwards, and after I run it, I want to send the payload. Also, just print out the payload. So where are we going to break? We're going to break right before we return, so main plus 149, main plus 149, and then we're going to do that. Send line R, waits warning, stopped. Send line, oh, I see. You have to send bytes. Stop process, user, local bin, pwn-debug. Okay. I'll see what we set up in this one previously, because there's a solve script previously. Send line run. Okay, that's the same. And then it's the same here. Okay, wait. But anyways, the main idea is we have our bytecode here, and then this return address points to the address of wherever we inserted the bytecode. And then we have this padding so that we actually overwrite the return address. I'll try to run the other script. If that one doesn't work, then we will just move on. But hopefully hopefully it works out. Oh, wait, I forgot. I have to make it interactive at the end. Yeah, okay. Okay, so we're here, and then where are we going to return to? So this is not the actual address of where buffer should be, 7FFF. If we examine this memory, this should be somewhere else. 20X. Oh wait, no, this is, okay, yeah, so this is where we inputted our stuff. Okay, so that's correct. 61, 61, 61, 61. Okay, oh, okay, this is at the very end, and then we have the code here, okay. So instead of A's, I am going to replace this with code that doesn't do anything. So I'm going to go to solution.py. This is padding, so the padding was A before, but A is not an instruction in assembly. So we have to change it to no operation, which is this value here, OX90. So this is what's called a NOP slide. It's essentially when we have our padding, but our padding is also instructions, so we don't want the padding to do anything. when we actually go into there. So we will try this. Okay, so that seems correct because now when we enter here, we have the knob slide. And then if we continue down, I'm not sure how many knobs there are. I'm gonna go next instruction, how many times? Okay, eventually we will get to the code though. Invalid instruction at somewhere here. Okay, I'll give another shot. For pointer, okay. What if we can do this? We can view the instructions here. So 40 instructions down is nothing. 160 instructions down, and we get some stuff here. So bad, jump creator, ADC, DHDR. Okay, this does not seem to be, okay, this is not the shellcode. Okay, I am going to see what we did in the other file. As it should be the same after read d4 0. I did print the pointer for the buffer beforehand. GDB challenge. Got end of file when reading in interactive. Shellcode f.read. Length of shellcode raw, and then okay, well, even if this doesn't work out, I hope you understand the conceptual part of it, which is just we want our program to return to the address of our shellcode. End of file when, okay, I could debug this, but I think I'll just move on. Sorry I couldn't finish that part, but there should be some other challenges later on. But yeah, if you want to actually, if you don't want to write your own shellcode, you could use this Python library, which is PwnTools that we've been using, and you can create your own shellcode for whatever you want. So you can create shellcode for catting the file flag. You can create your own shellcode for spawning a shell. And then this is going to be the actual assembly version, but it's also in bytes. So you can just directly send this to your program. Instead of opening it from a file, you could just create them from here as well. And yeah, so there's a few problems if you let your program execute the shellcode directly. So we have something called no executable bits. So the basic idea is we don't want all of memory to be both writable and executable. We want it to either be writable or executable, but not both. So this is called write XOR executable. And this is what we have in modern programs. So before we have the no executable version, everything can be both writable and executable. But afterwards, we define certain segments of our program to be executable and also certain parts of our program to be writable. So we can write actual data. We should be able to write to the stack and a heap, but we shouldn't be able to execute any parts of our program that are in the text and also we shouldn't be able to execute parts of our program that are in the stack or the heap because it's writable. But we should be able to execute libraries and the text. Not data though. Actually, it should only be the text segment that's executable. There are a few parts of your program that are both writable and executable. So these are exceptions to the write or executable rule. The parts of the program that might have this is a part of the program responsible for JIT. And JIT is a functionality. It's used in interpreters where you have a lot of instructions that are very commonly being executed, and you want to compile those common programs. So you need to write the compiled version of that instructions, like those instructions that you are commonly seeing. You want to be able to write it to some section, and it's also code, so you want to be able to execute that as well. So an example section of the program that is both writable and executable is the JIT section. And this is what you can do to exploit that. You can create a bunch of constants somewhere. If your program can allow input, you want to create some constants in your code that can be JITted. And then when it's JITted, it will be converted into this assembly here, which has a portion of it that when you read it, when you read this portion here, this sub portion of whatever our machine code is, if you read this subsection here, it disassembles to this part here, which is the assembly for the syscall of exits. So this is bad because you could define some constants and then they get assembled, and then you have some code that you can execute that can do malicious things. Okay, this is the second half. So I might take a break here, 10-minute break, and then we can go into some of the more exciting stuff, which is return-oriented programming. So we'll take a 10-minute break, and hopefully we can finish in time as well.
Okay, so now we're going to cover return-oriented programming. And return-oriented programming is one of the things that we can use to bypass the no execute or read or execute rules. So essentially, what we're going to be doing is we're going to be abusing this library called libc. Well, it's a shared object. So the shared object contains a lot of useful functionality like network communication, opening sockets, setting up processes, all string operations or signals or file I/O. We're just managing memory. A bunch of useful operating system stuff. You're going to be using libc for that. So libc is somewhere in your system. It could be in the lib folder or the user lib folder or the lib64 folder. You can also download older versions of libc. Libc is a shared object, so a shared object can be used through different languages. It doesn't have to be C. It can also be other languages like Ruby or Lua or R. They can all depend on libc if they want to have some of the features that it has, like file I/O or memory allocation and stuff like that. So there's this function finder. If you have, let's say, a symbol of some part of libc that you don't know what it is, well, you can actually find the version of libc that you want. And you're going to want certain versions of libc because certain types of programs depend on certain parts of libc or like certain versions of libc. So yeah, so this might be why you want to do that. I omitted a slide here, but it's like you can actually open a slideshow and just see how you can download different versions of libc. But yeah, return-oriented programming. So the main idea behind return-oriented programming is we want to bypass the no execute rule by using functions, so library functions, that are already allowed to be executed. So you can execute library functions. You can't write to them, but you can obviously execute them. And the main idea is that we locate something called a rob gadget. And a rob gadget is just a segment of code in your libraries or in your code section that ends with a return. So it has a few instructions before a return. So essentially what we want to do is we want to use these atomic rob gadgets, like these very small rob gadgets, combine them together to form some larger functionality. So here's an example. This is what's called a rob chain. A rob chain is a collection of rob gadgets, and we put them onto the stack. So let's say somewhere along the line we trigger a stack overflow, and we can override a few addresses onto the stack. So we can override the return address to be pointing to the first, to be like a pointer to the address of our first ROP gadget. The second one can be pointer to the second ROP gadget, and then our third one is pointer to the last ROP gadget. So what will happen is that when we execute the function, we're going to return to the return address, which is this address right here, which is the first ROP gadget, and this ROP gadget will continue on with Zora EAX, increment EAX, and then return. And when it returns, it's going to go to our second address down here, which is this ROP gadget here, which is going to move 0 into EBX and then return, and then obviously returns, and then it checks the next thing to return to, like this is the return address because it's at the top of the stack now. So after we do that, we're going to be doing syscall and then return. So in total, it's going to be running all of these operations, and then this is like all this code, like Zora EAX, increment EAX, move EBX by 0, and syscall. This is how you call exit. Like you can call this syscall exit and exit out of the program. So here's an example. I think I might have time to actually explain this. Maybe I can solve it. No, maybe. Okay, I'm gonna explain the solution because I don't want to spend time solving it. Because I want to go sleep. But we'll see what happens here. So I'll explain what this code is actually doing. We have this win function, obviously, that we want to call, and once we call it, we would call system bin sh, which is obviously that's how we get a shell. What we want to do is we want to somehow set can open to be true, and we also want to set our arguments, which is key, equal to 1337 for us to be able to do this. Obviously, there are different ways to possibly call system. Like if you actually look at the assembly, you could find the code that is after the check, so like after the check, and you can just jump there. But for sake of like learning, we're going to do it the proper way and use a ROP chain. So we're actually going to set can open to be true, and we're going to set key equal to 1337. So let's try to do this. I am going to have to let's open up, what is it called? I want to open up Ubuntu. And there was like a problem with the first challenge, which was about stack alignment. So we can talk about that right now. On 64-bit systems, specifically 64-bit systems, there are certain issues with libc. So like when I actually did the challenge, I did it on Arch Linux, which has the newest version of libc, but my libc version here on WSL is going to be different, and it changes based on the x86 sys5 ABI. So what happens is when you have a call like system, your stack needs to be aligned to have 16 bytes on the 16-byte alignment on a call instruction. So when we actually called, actually did the syscall, it wasn't aligned. So what we had to do was place a singular red gadgets beforehand. So that was the problem with the initial challenge, and it was TJ called out it. But yeah, so we're gonna, what is it called? We're gonna go here, and we're gonna go into ROP, and then we're going to take a look at this. Yeah, it's the exact same challenge. Okay. Now, like, if you have trouble making a file, like, here's the make file, and we can just make all. And essentially, what's happening with here is like, in my make file, I have a rule which is all, and all will have to build challenge, and in challenge will have to build challenge.c if it's not already in my thing. But yeah. I'm also, what I'm doing, okay, so this make file is doing something a little bit different. It is also, what is it doing? It is creating a object file and linking that as well. This is like a helper thing because the challenge would be a lot more difficult to do if we didn't have this helper thing. And let me just explain what helper.s is doing. All it's doing is it's adding this little piece of code right here, pop rdn return. So we can see that later on, but I'm going to make it. Should actually be choosing full screen. Okay, it's fine. Okay, so GDB challenge, and what I'm gonna do, do I have tmux? Okay, I have tmux here. Let's split the pane. So I'm going to run challenge, and I also want to at the same time make a I want to, what is it called? I want to make a solution as well. So p equals process challenge. So for the current one, p dot send line. We don't know what it is, but we're gonna send payload. Payload. Okay, whatever. Okay, so. Oh no, I do not want to use GDB. I want to use pwn-debug challenge. Okay, so right. So first thing I want to do is I want to trigger a buffer overflow. So what I want to do is I want to find how much data I need to put into the buffer to actually give me the overflow. Like, okay, you can calculate this by hand, but I don't want to because, well, you know what, I should learn how to do it by hand. I'm pretty sure it's just going to be the same as the previous one that we were using, which is 120, but just in case, I am going to break right before return. So I'm going to run Python free import pwn.cyclic. Oh, okay. So Ubuntu has to have a different package manager. You can't use like you have to use ven. So that is that. Then free import then pwn.cyclic 256. It's like 256 is just like how many characters I want. Like I could do like 25, but yeah. Okay, so oh man, how do you even select this? Okay, you know what? I'm gonna just do a different terminal. I do not like tmux, but okay. Oh. Okay. Okay, Python free import pwn.cyclic. Okay. Okay. So what is happening here? Okay. So I'm gonna go next instruction 2 times, and then I want to print RSP. Or no, XRSP, sorry. So this is the actual return address that it's going to be going to. So that looks like 120. How do I know it's 120? Well, it's just because I memorized that this string is 120. But like, if you want to actually confirm yourself, then you can like do this. Yeah. So it's 120 from the offset. Okay. Let's go back here. So what is our payload going to be? Well, payload equals, let's just set like some random arbitrary value. Like, why do we make it 8? There's no reason. It's just an arbitrary. It's just non-zero. It's like anything. That's gonna be 1 byte anyways. Okay. So this is what that's gonna be. Maybe I should do this. I can make it multi-line. Plus some byte of wherever we're going to return to. So where are we going to return to? The address that we put here is where we're going to be returning to. So let's see. Just note here that this is a position independent executable. So like the address is always going to be the same. If you have a global allocation table, it's probably nicer, but even that could be randomized. So anyways, let's see what you have. Where are we returning to? Oh no, info. Okay, you know what? I can just do object dump -d -m -m Intel challenge. What do these flags mean? Okay, so D is dump like everything, and then M is like the syntax, which we're doing Intel. So okay. You know what? Grep. What is it called? What is the function called? Set open. Here it is. Okay, so this is the actual address of set open. So we're going to copy that and we're going to put it here, 1.p64, and then this address right here. So we're going to do that. Okay, we're going to do that. Okay, what else are we going to do? Well, after we call this function, we need to do something else, which is we need to set key equal to 1337. So how are we going to do that? Well, we have to use a rob gadget for that because there's no function that would actually allow us to set anything to be like that. So we need to do a rob gadget. Now, let's try to find something that affects the input arguments. Remember that if we go all the way back to the start, we had calling conventions. So somewhere here, calling conventions was somewhere here. Sysp. Okay. So calling conventions. So the first argument is actually passed through RDI. So somehow we need to change the value of RDI before we actually call the function. And that would be our arguments, right? So let's go back to where we were at before. Okay, so yeah, so we need to change RDI. Now, what we can use is we can use a tool called rob gadget, and we can specify that the binary that we want to search for robs is challenge, and then we want to search for, so we're going to grep and filter for the regex containing RDI. So I have to activate venv. Oh man, venv bin activate. And like, okay, so like you're probably seeing like a few issues in the video if you're even watching this. Like my system's just slow. Like it's not any like codec error or anything like that. The system is just really slow. But yeah, binary equals challenge, and then what do you have after that? Binary equals challenge grep RDI. So we're searching for instances of RDI. Now this is all that we get. So which one of these can actually change the value of RDI? Well, okay, let's take a look at this one. What we're doing is we're doing an OR, and then we're taking RDI and we're adding an offset to it. And then we're jumping somewhere else. And we're not even returning, we're jumping somewhere else. So we're not gonna use this. What is this? Well, we have an OR about EBP and then RDI. So we're not even changing RDI here. We do have pop RDI, and this is something that I added that I talked about previously. We have this one, shift the pointer. So I mean, like RDI is pointing to something by 1. So I mean, the only one that we're really going to use is this one. So let me copy this. But yeah, so let me copy this. Now here's the interesting thing that we have to think about is how are we going to get the value that we want to push onto the stack? Well, we'll think about that right here. So let me do this. Okay. Now, what you want to know is that every time I call return, well, well, every time I like enter a function, this value is going to be off the stack. So like, let's say this is at the top of the stack right now, like this is the return address, because at the end of a function, remember, like RSP is reset. So like all of like the stack frame is reset, and then like you only have the return here. So like this is going to be at the top of the stack, and then like when I call, this is going to be gone. So then this is going to be at the top of the stack. So like the same is here. So like when I call this, this is going to be gone. And then what's going to be at the top of the stack? Well, something else that I put down here. And so this is going to be at the top of the stack. Now, what does pop do? Pop takes the value at the top of the stack and it puts it into RDI. So when I do this, I am essentially putting the value of 1337 into RDI. So that is that. Okay, the last thing we have to do is we have to go back to our original function, which is win, right? We want to go to win, the win function. And so win. Okay, so this is the address of win. Now, hopefully, send line payload mp interactive. So like after we send a line, we want to have it to be interactive so we can actually play around with it. So hopefully this is correct. I've been having a lot of issue actually solving these challenges, so I hope this works. Process O. I keep on forgetting that there's a namespace, but okay. No. Okay. Okay. Oh, thank God. Okay, so we actually have root now. So like this is, we just want to show. Oh my God, that's awesome. Okay, so thank God, we actually solved the challenge. That is great. If there was some bug, I would have been so sad. But okay, so that's the ROP challenge. Hopefully you understood that one. We're gonna go talk about something else now. Is this recording? Yes, it is. Wait, how far are we? 20 minutes. That is not good. But we'll continue on, and we'll talk about finding gadgets. So you probably already saw how to find a gadget. You have to use ROP gadget, say whatever binary you're using, and then grep for the actual value that you want, like the actual thing that you're concerned about. You can also use ROP gadget to generate a ROP chain. Last time I tried it, it didn't really work out that well. But if you have like some statically linked libc, then it actually probably works kind of well. Or if it even just knows like where libc is living, it could probably tell you as well. But if you just have like a strip program with like dynamically linked libc, well, the addresses aren't going to be there, so it's not going to know. So that's going to kind of suck. But yeah. Okay, stack pivoting. So stack pivoting is a certain technique where you can actually use ROP gadgets to change RSP. And why do you want to do this? Well, you might want to do this if your stack is too small, and like you can't corrupt other parts of the stack. You just want to change your stack to be somewhere else. And so you can change RSP. You can pop RSP and return. You can pop RDX, and then exchange some other value. Oh, sorry, this should be RDX. This should be RDX, and this is a typo. But you exchange RDX and RSP. There's also a method that you can do with leave, which was mentioned in some hack tricks article at the very end, but it's some really arcane and weird technique. But yeah. Okay. What now? Okay, magic gadgets. So let's check the recording. Okay, this is still working. So magic gadgets are simple gadgets that can be used to win a challenge. So like we did a whole ROP chain, right? And like our ROP chain was simple. Like the ROP chain that we used to solve the challenge was actually kind of simple. You can have ROP chains that go really, really long. So sometimes it's nice to find any gadget that can be used to like immediately win a challenge, like whether that be opening a shell or reading a file or changing permissions. So there's this tool with one gadget. I haven't actually used it, but it should essentially search your binary if you have any of these magic gadgets. So there's a mitigation, and it's called control enforcement technology. So what it does is it prevents you from jumping anywhere you want. Essentially, the only places that you can jump is this end branch 64 instruction. So if you, let's say you have like a jump, like a call jump, to like some function, if you call and like if you jump to any instruction that's not an end branch 64, then the program will raise an exception and crash. Now the problem with the end branch 64 is that it's at the very top of these functions, or these sections. It's at the very top of it. So if you are, you want to craft a ROP chain, well, you have all of these instructions here that you just don't want and can like corrupt your overall state of things. Like you want your gadgets to be as close as return as possible so that you have atomic instructions to work with. But then like if you have end branch all the way at the top, you're not really going to have that. So that's something that is implemented in newer chips, that is going to be problematic for ROP, return-oriented programming. And there are obviously bypasses for this. Like there's block-oriented programming where you have entire blocks, and then you would program with the entire blocks. But a lot of it's theoretical. All right, let's talk about the heap. So the heap is a notoriously difficult thing to understand. I don't really understand it in depth, but I'm going to explain what I know of it. So the heap, as you might have heard, is a place where we store memory. It's part of like the actual virtual memory that a process gets when it's run, and it is for dynamically allocated data. So like let's say you have a list that can either like grow or shrink depending on how many items are in it. So like you can allocate that on a heap. That's actually what a vector is. It's like a list, but it like doubles in size every single time you add a new data point. You can also use it for data shared between functions. So like let's say you want to return a pointer or something, and like when you exit the function, well, your stack is gone, so you don't have that data anymore, so you want to store it into the heap. So how does the heap work? Well, there are two functions. There's malloc, which would allocate a portion of the memory and return a pointer to the memory chunk, and then there's also free, which would it wouldn't like, okay, so it would just return that memory back to like the program, so like any other mallocs can use that area as well. And so free is problematic and malloc is also problematic, but yeah. So here's like a TLDR. If you're a developer and you want to know how to use the heap properly, like a lot of these are things that are like taken to be just bad practice in developers, and developer like just don't do these things. Do not read or write bytes at the end of an allocation. Do not write to a pointer that is returned by malloc after a pointer has been passed back to free. We'll see why this is the case. Like we'll understand what a use after free is in the next slide. In a few slides from now. But yeah. So the heap allocator. So like oops. I really hope I didn't just skip a few slides. Okay. All right, heap allocator. So heap allocator is like the specific implementation of malloc and free. So like not every single program is going to use the same libraries. So we're going to use glibcmalloc for Linux, but there's other heap allocators as well. Like there's segment heap for Chrome. There's a kmalloc for the Linux kernel, which you might need to know if you want to do kernel pwn, but I'm not sure. But we're going to talk about glibcmalloc. It's inspired by something called ptmalloc, and ptmalloc is something that introduced this idea of Fred local. It was one of the early adopters of Fred local heap. Okay, so glibcmalloc is the heap allocator for Linux, and it's good for multi-threading, obviously. So there are a lot of changes. There's like a ton of changes that are happening to glibcmalloc every single time. So knowledge about one version of heap is completely different than knowledge of another version of heap, which is why we kind of are so heavy on understanding libc versions or glibc versions, because it honestly depends based off that. But yeah, there are frequent like changes to glibc malloc or like any allocator because there's like a trade-off between performance and security. Like people find a better optimized way to do things, but then security says that okay, what you did assumed a little bit too much. Like you can't have optimization without assumption, and if you have assumptions, usually you have some security holes that are going to rise because of it. So you kind of have this back and forth between updates that are introducing security patches and also updates that are introducing um, performance updates because the security slowed things down. So let's talk about it. So how does glibc create a heap? Well, the heap is only created once the first malloc is called. So like you can see on the left, this is the program memory before malloc, and this is the program memory after malloc. You get the heap. So by default, the heap is this macro, the C macro, default mmap threshold. And depending on the threshold, you have different syscalls that are called. So if you're interested, you can run strace on the malloc, and you can see, okay, it uses mmap if the size is bigger than the threshold, and it uses break and sbreak if the size is smaller than it. Okay, so what is malloc actually doing? Well, the malloc is supposed to return some portion of memory that the user can use to write some cross-function data. So how do we actually get this actual value here? Well, you have to first check a free list, and we'll get into what a free list is later. Otherwise, you create a new heap chunk. So in our program, we have all of the memory that we can give, all of the available memory that we can give as a chunk that is like the entire size of the heap. It's like when you create it, this is the entire size of the heap, like by default it's 21,000 hex. But then like we're allocating a size, and then we are allocating a size, we're going to break off a piece of the top chunk. So we're going to get like a subsection of the top chunk, and then we're going to give that back to the user. And we're going to break it off, and the size of this chunk is going to be the word aligned size plus some metadata as well. And malloc just returns a pointer to this heap chunk that we just broke off from the top chunk. It's going to give us that. So the heap chunk is, this is what it is. So like it has metadata at the top, and then it has user data at the bottom. So there are like two different types. There's an allocated chunk, and there's also a freed chunk. And it's all in the same struct. So like I'll go to the next slide later, but it's all in the same struct. It's just like different sorts of metadata are used depending on if it's allocated or freed. And yeah, so you have like some metadata here, like the size of the previous chunk, which is used for coalescing, but we don't have to get into that. You have size of the user data, and then also a few bits here, like having been freed, was this mmapped, and and some more stuff. So we'll continue on. So this is the actual struct definition. You can see like a few things are only true if the chunk is free. So like these are metadata that only exist if the chunk is freed. And yeah, okay. What's happening here? Okay, so free. Okay, whenever free is called, we're going to take the current chunk that we were given, so like the pointer to the chunk, we're going to move that into a free bin. Now, what is a bin? Well, a bin is essentially a linked list of chunks, but they're free chunks. So like the chunk that we had before was like allocated type, now becomes a free type, right? So like it's the same struct, but like this was allocated, now it's become freed. So it's a linked list of those freed chunks. And the capacity of the bin, like there can be an upper limit, it depends. So like there are a few types of bins. We're going to go over the first one, which is a Tcache bin. A Tcache bin only contains chunks that are between this size, and you can only have a maximum of 7 of these chunks. So it's made for small allocations. So like if you have a small allocation and then you free it, you're going to get a chunk like this and a chunk like this. It's like a linked list of chunks. So like you free once and then you get something in your linked list, and then the next one is going to be something else in your linked list, and then so on and so forth. And it's a singly linked list, so that means only forward pointers. Yeah. There's this like side note here which I don't really understand, but like apparently the first malloc that you do will also add in like an other chunk that's 300 hex bytes, but we don't have to worry about that. For conceptually, we don't have to worry about that. Okay, the other type of bin is fast bin. So the fast bin is every time we free a chunk, but like we don't have any more size in the Tcache bin, we're going to use the fast bin. So the fast bin is going to contain chunks of like the same size as what is it? The same size as the Tcache bin, but there's still a maximum. And it's also simply a linked list, but it only has forward pointers as well. So yeah, there's unsorted bins. So the unsorted bin occurs when you have a chunk size that's bigger than the other ones, and there's also no maximum. And this one's also a doubly circular linked list. So they're backwards and forward pointers. So there are two other bin types. Well, there's like a lot more bin types, but like these are the ones that we're only going to be covering today. If you want to like learn more about the heap, there's there's a good sig pony lecture on it. There's also like some pwn caller stuff as well. But yeah, so we're going to go for a walkthrough of how memory is actually allocated onto the heap. So we're starting at main, so we haven't done anything yet, and we're going to go to next one. So in the next one we have malloc. So once we call malloc, the heap is created. The first malloc call will create the heap, and then the malloc also has requesting a size of 0x20. We're going to give it 0x30 because we need to have 16 bytes of metadata. But yeah, so we have this allocated chunk that has a 0x30 in size, and that this is like broken from the top of the top chunk. So like the top chunk that has all the memory, we're going to be like taking a little bit of that, we're going to be breaking off a portion of that for the chunk here, and we're going to be returning it as a result to the malloc call. So let's go to the next slide. Next slide here, we're allocating something a little bit larger, 0x420, and then this is again, it's going to eat away from the top chunk, so it's going to eat away 0x4. Is it the size? Okay, actually, I think it should be a little bit bigger than the size 0x430. I should change that in the slides later on, but it's going to allocate a little bit bigger of a size, and then well, we go to the next one, and you can sort of guess what happens there. We're going to allocate some other chunk and return that. Okay, here's where the interesting thing happens. So the first free that we call, well, we're going to mark this chunk as free, and then we are going to add this chunk into the Tcache bin. Why is it the Tcache bin? Well, the size is between 0x20 and 0xb0, so it actually belongs in a Tcache bin. So we're going to be adding to the Tcache bin. And then the second free, well, the chunk that we free for B is actually a little bit bigger, and it actually belongs to the unsorted bin. So we're going to set up the unsorted bin to points. So the first element is now going to be chunk B. And chunk C, once you free chunk C, you're going to be adding to the linked list because chunk C has the size of Tcache. So we're going to be adding it to the Tcache bin, and it's going to be at the end of the linked list as well. So you can sort of see how this happens here. Now the interesting thing, we're going to have this D here, and we want to malloc that. So what are we going to do? Well, we already have something of similar size in a Tcache bin, so we're just going to give it that. So we got the first element of the Tcache bin, and we gave that to chunk D, and now chunk D is on a heap, and chunk A that was on the Tcache bin is now gone. So that's sort of walk through the heap. And yeah, so what do we have next? Okay, use after free. So this is the main vulnerability. You see in a lot of like actual, like this bug is pretty common. Like I think Redis had a use after free bug like a few months ago. But it's very common. I make this bug a lot, but we're gonna talk about it. So it's a vulnerability that exists when a program uses data that's previously freed. So remember, like when we're allocating D, we have this like previous one here, like it came from the Tcache bin, and we can just get the same heap chunk back, like the same address and everything. So if, for example, you have a pointer that's pointing to allocated chunk, and then you free that chunk, and you get like another access to the same chunk. Well, you have now two pointers. You have two pointers that are pointing to the same thing, and this can cause a lot of issues. So it's the programmer's job to set the pointer to null after a free call. And yeah, so this is kind of an example, but not really, but like it kind of is, because there are two pointers to the same region of memory that can cause like a lot of issues. So you can see, if you can try to understand this challenge, um, there's a +4 because I was getting issues with cross architecture things, but um, I'll just show you the solution. It's like a very simple solution, and I can walk you through why it works, but it's literally just okay. Can I run this challenge? Okay, so what's happening here? Well, what malloc does is what m does is it allocates like a region of memory, and then when I call free on it, I'm going to free this memory, and then at the win function, I'm going to malloc the same piece of memory, so I have the same data. So I'm getting the same heap back, and like the previous data that I put inside of cur buffer is going to be the same data that I get when I malloc this back. So let's just show that in action. 1337. And I'm going to free this, and I'm going to try to win. And well, I don't know what this is, but this is, oh, okay, actually no, we got a shell. Okay, yeah, we got a shell. So okay, so we just won. Yeah, we just won. Okay. There is a slide about safe linking, which is like a protection against it. But I think I hid it, so something I should not hide it. Did I hide it? Safe linking. Okay. Anyway, safe linking is like the thing that would actually prevent this. So like in libc 2.32, you can't do this because the pointers are going to be encrypted by the randomness of ASLR. So you won't actually be able to, well, well, there's a mitigation against it. I'm not actually exactly sure why it works, but this is the mitigation against it. So I'll talk about a double free. Double free, when I explained it, was kind of confusing, so I'll try my best to explain it in like a different way. So like this is the same thing as a use after free. Hopefully I can like make it bigger, but yeah, this is the same thing as a use after free, but it's setting up a use after free a lot easier, because all you have to do is you have to malloc 2 times, and you get like 2 pointers to the same chunk. So essentially, what you do is you have like, you malloc something, but then you free it 2 times. And so like the first time you malloc, you get this chunk, and the second time you malloc, you also get this chunk. So you have 2 pointers to the same chunk. And so that causes like the same issue as a use after free. Now in modern like libraries, there's actually like that previous example might not actually work, but there is a variant of a double free called a staggered double free, and this is something that like I learned from this YouTube video. What it is it's a double free. Essentially, you have mallocing first thing, you malloc the first thing, and you free it, so it's now in the bin. So A is now in the bin, and then okay, this should say now, not. It should say now. But then you have B, and then you malloc the same thing. So now you have the chunk. So like it's pointing to the same chunk as A, and then you free A, but then you also free you free B, but then you also free A. So essentially, like they're pointing to the same thing. So you free it 2 times, and now you have a double free. So that can be very problematic. Okay, the other class of vulnerability that we're going to be talking about is a heap overflow. So this is kind of simple to understand. It's similar to buffer overflow, but it's for the heap. So like, let's say that we have two contiguous, like they're beside each other, like we malloc things and they're right beside each other. Because this is like how it actually works. Like maybe I can just show you, I can show you right now. Yeah, why not? We have time. Temp C and main. return 0, include split of h, int a equals pointer malloc 0x30, and then we're gonna get b, and then like I don't know. We're just gonna do that. I'm gonna gcc temp c temp. Okay, so let's go into temp. Let's just I don't want to use GDB temp. Okay, so we are going to set a breakpoint at main, and we're going to run. And well, let's see what's happening here. So let me change the actual size of whatever this is to be like a little bit smaller. Like it's a new bond here, right? Appearance, and then I want to change this to 14, so it's actually a little bit like nicer. Okay, so we're here right now. I'm gonna call this malloc, and I'm gonna call this malloc, and then I'm going to show you the heap after that. So okay, we have to keep on going down. Okay, so I'm pretty sure we just called like that malloc. Where are we right now? Okay, we're right here. So we just called both of the mallocs. So now I'm gonna show you the heap. Okay, so this is the heap. Like look at this address right here. 0 okay, 55559290, and in this one 555592 D0. So they're right beside each other, right? Because like this is size 40, and you add 40 here and you get D0. So they're right beside each other. So obviously like some of it has like metadata, but like you can also overwrite the metadata. And yeah, so what I'm doing here is like I have two of these allocated heap chunks to right beside each other. They also have metadata, but like what I do is I string copy, and string copy is a function that doesn't actually check the heap size, so it just like blindly copies things. So like the argument that I give it is going to be going into A, but then like we exceed A's buffer, and then we actually end up overwriting B. So like you can see B's value like initially, but then after we string copy, B's value is now a, like it's overflowed a bit into A. So yeah, there's also like this is something that Jackie wanted to mention is a lot of like a very common way that you can actually do a heap overflow is with V tables. So like V tables are essentially where your functions are. Like when you're doing dynamic dispatch, you have V tables, and they're like I guess like somehow you can do a heap overflow with those, but I haven't worked with that actually, but like apparently they're very common to trigger heap overflows as well. And so okay, now we're going to talk about T-cache poisoning, which is a pretty common exploit that you can actually do. So the idea is like you want to allocate two chunks. Sorry, it's a combination of use after free and heap overflow. And so the idea is that you want to be able to get like an address anywhere, like anywhere you want, and just have like an access to that address. Well, what you can do is you can allocate two chunks to the heap, or like not even an address, just like any single data, like arbitrary rights, pretty much. What you can do is you can allocate two chunks to the heap. Then you free the two chunks and like you get them into the T-cache bin. Then you do a use after free. So like assuming you have a pointer still to this freed value, well then you would overflow, like you do a heap overflow, and you overwrite the second free chunk data with your data. It's like whatever data that you want. And then you malloc again to get the second bin's data, and now like the actual data that you get back is going to be corrupted. It's going to be like whatever you did previously, whatever you added to the overflow, that's going to be your data. So because like when you malloc, you just get it from the bin if the size is correct. So that is Tcache poisoning. And yeah, so we're done with heap. Like there's a lot more stuff with heap that we didn't actually cover. Like there's this whole idea of memory data corruption, and that leads into people making their own houses, which are essentially challenges that, or like specific things, or like specific just exploitation techniques. But we won't go into that because that is too much. So we'll talk about like the final few techniques. They're like low hanging fruit, but they're worth mentioning. So there are format string vulnerabilities. It is like a vulnerability with printf, where you can actually leak values off to the stack. So like you can provide arguments that are, I mean, like scanf, you can provide arguments that are from the stack. So like %x would read hex bytes off the stack, %d would read decimal bytes, and then %p could read entire pointers off of the stack. And %d allows you to overwrite previous memory onto the stack as well. So format strings are kind of a weird vulnerability. Um, like like it exists, and you can leak some stuff. You can leak stack canaries, you can leak addresses with it. You can do some pretty cool stuff with it. So anytime you see like a scanf printf, you can sort of think about a format string. And yeah, integer overflows are these attacks where you have unsigned integers or signed integers, and if they become too big in size, then you would either wrap back to 0 or you would wrap to a very large negative number. So that exists. And the last one is array indexing. So you probably like did this before at some point in your life as an off by one error when you're actually like learning C for the first time. Arrays do not actually check how far they are. Like you can write outside of an array. And like this is because an array is just a pointer under the hood. So you can literally just change, like you can have like an index that's like 5 million, and that's still going to be readable. You might get like a segmentation fault, but like if it was like a smaller value, like let's say like 18, you could write like around, like you could write after the buffer that you should be allowed to, and you can overflow into something else as well. So yeah, so that's everything that we had to cover today. And there are some resources, like Plum College is really good. There's a few war games here. There is, if you want to understand program memory, this is like well, this is ELF. This is the ELF memory actually looks like. There are hack tricks. So hack tricks, I'm pretty sure like most of these are the same book. They're just like copies. Ironstone has like a really good book on like a bunch of exploitation techniques. There's this idea of the heap. So like there's this formal resource about the heap. There's a Sick Pony, which I used for a lot of this to just learn from. There's also well, I'm not sure what this YouTube channel is. I think he does some work. libc. So like if you want like other ways to download different libc versions, you can go to these sites as well. And the last thing I want to mention is apparently there's this like very, this is a pwn psychology. So like the philosophy of a pwn player is like you have two primitives. You can either use a pointer to write or to free, so like do arbitrary write, and then you can use a pointer to read, and then from that you can either like modify code or pointers or data as variables, and just everything in pwn is dependent on arbitrary writes or arbitrary reads, and you can get past anything like that. Like you just chain these things together. You saw some of the power with that in return-oriented programming. Even like heap overflows, like they seem like small sort of steps, but like you have to chain them together to achieve great things. So yeah, so this is we'll just finish off right here. Yeah.